I'm going to discuss the fluidic process to massive transfer of the tiny LEDs on the silicon substrate. Okay, title of this talk is the high accuracy electrofluidic process for the display application, specifically focusing on the AR, VR displays, which need the high density integration of the LEDs on the substrate. So Advanced is early stage startup. So 5 years, I founded the Advanced View in 2019. So we recently closed the pre-A, and then hoping to the open for the other funding for later this year. So I think I'm assuming that most of you are familiar with this slide. So MicroLED are really tiny inorganic LED is high brightness and then self-emitting device. So hopefully it'll overcome some limitation of the OLED, and also it has some advantage over the like high contrast and brightness, and then robustness of the display pixel compared to the organic counterparts. But the downside of the micro-LED is that we need to move the millions of the maybe tens of millions of the pixels on the display backplane. So we need a massive transfer or pixelation of the micro-LED on the glass or silicon substrate, depending on the application for like mobile and then AR, VR displays. So if you really pay attention to what's the key limitation of the micro-LED industry, which is the high yield and low cost assembly and pixelation of micro-LED for the mobile and XR displays. So I'm going to discuss on the our unique approach to tackle these problems. So this is really old data, but people are actually forecasting that the market of micro display is at least expanding, and then it actually can be used for smartphones, smart tablets, and AR, MR, also large TV and automotive. But there's some like conventional approach to use the pick and place and then electrofluidic process. So they can use the electrostatic head. So they can actually pick up the micro-LED from the substrate and move to the donor substrate, which is going to be display backplane, and they can use the elastomer and then ledge illumination, which was the presented by the previous the speakers. And also the fluidic process and eRooks and Samsung, LG actually demonstrate the possibility of the fluidic process. And then, so Lab 3 actually approach relies on the intuitive actually picking up the micro-LED and then transporting to the substrate, but it'll actually needs multiple release and then transfer process. But the fluidic process, they use the fluidic motion to assemble the micro-LEDs on the substrate, but it's not really intuitively straightforward. So it'll have some probability to the lose the micro-LED and then miss on the micro-LEDs on the target locations. So I'm actually looking at the nano-LED. It'll use only one single process. So preparing the nano-LED COW, which means that vertically either top-down processed or bottom-up grown nano-LED on the substrate, we can produce like millions or tens of millions of the billions of the nano-LEDs on the 4-inch wafer. The chip cost is much lower than the conventional process, because if you grow the epi wafer, and then if you actually pattern the really tiny LEDs, which means that it'll consume less epi wafer area, okay? And then from the nano-LED COW, and then we can actually assemble them not only on the display backplane, which lowers the chip cost, also assembly cost. That's our unique process. So this actually illustrates how we can tackle, address the key limitation of the micro-LED process. We actually prepare the nano-LED ink. Maybe it could be like indium gallium nitride and then aluminum indium phosphide for the LED emission. And then we break them and then we put in the solution. And then we use our predictive process. And then I'm going to actually discuss our key result on the later on this presentation. We can